Hey! Alright, welcome to my channel. Today we're exploring an absolutely fascinating subject, how light can be frozen, how it can be made to stand still, and what that really means. Watch the video until the end to see each idea step by step and most importantly, to better understand the reality and the mystery behind light that stands still. What is the world made of? What is it composed of? This is an age-old question. Unfortunately, most of the time we give the wrong answers to this question because we don't understand the scientific method. A common mistake is to imagine photons, the particles of light, as little balls when light is made to stand still. For example, we imagine those photons as little balls that are stopped from their movement and then set in motion again. The mistake is to consider the world as being absolutely made up of solid objects when in fact we don't really know what reality itself is. And everything could just be a mathematical model. In the case of the electron, another example, it can be a ball, an electromagnetic field, or a packet of energy depending on the context. In fact, we don't really know what the electron is. We describe it each time with a different mathematical model, and that's why we interpret it differently. We end up believing that it's a ball, a field, or a packet of energy. In fact, we don't know what we are. In a way, like a cat that gradually finds out how things are, slowly we discover that reality is much more complex than we would think. Have you ever wondered why light slows in materials? We know that the effect is due to the refractive index because the speed of light is c divided by n. C is the speed of light in a vacuum and n is the refractive index. Because of this, for example, a spoon looks bent in water. But we know that light is made up of particles called photons. So does that mean that when light enters materials and slows down, we should imagine the photons as particles that slow down? The short answer is no. Look, here's how we can understand it. The electric field of light polarizes the material it passes through, and the distance between the positive and negative electric charges of the atoms and molecules oscillates in sync with the electromagnetic field of the light. This oscillation of the charges produces a correction electric field with the same frequency, but out of phase, which when added to the initial field of the light, it shifts the total wave out of phase, making the wavefront advance more slowly. Simply put, the wavefront now moves at a lower speed and light travels more slowly. How do we interpret the same phenomenon with light particles, that is photons? Well, we say that the photons are continuously absorbed and re-emitted by the structure of the material. This makes them appear slowed down because they are stopped in place and released with a delay. Remember, it's not the same photon emitted after absorption by molecules, it's a new one each time. The original photons aren't delayed, new photons are generated, creating the illusion of slower movement. A good example is the lights on a Christmas tree. The light appears to move one way. In fact, it's the LEDs lighting up one after another. There's no actual light object moving along the string. That's an interpretation made by our brain. It's the same with how light passes through materials. We need to understand that the photon is not a solid object in the classical sense, but rather an excitation of the electromagnetic field, meaning a mathematical object. Photons are constantly absorbed and re-emitted. Who can tell which was the original? Making light stand still is something extremely special. How can light, which travels at the highest speed in the universe, stand still? But this isn't something new. Here's an experiment from the year 2013. Here, researchers trapped the light from a laser inside a crystal and after a minute, released it again. The light stayed there for a minute, effectively frozen in the crystal. But is that really the case? Let's see. In the experiment, the laser light was absorbed by a crystal containing praseodymium, which made the crystal opaque. The absorption of light excited some collective oscillations of the atom's spins, called spin waves in English. Basically, the light was captured in these collective oscillations of the atom's spins. After a minute, here's the trick. The crystal was a special one. At the command of another control laser, the crystal became transparent. Basically, the light remained trapped in the excitations of the atom's spin waves until the control laser was turned on, the one that restored the crystal's transparency. Now, the oscillations of the atom's spins de-excited and released the light they had captured. With the crystal being transparent on command, it allowed the light to exit the crystal. If that's not magic, then what is? But hey, you've learned that light isn't made of objects, but objects are our interpretation as much as it is at a given moment. Because the light that was released from the crystal is the same light that initially entered the crystal, it's not other photons emitted by the de-excitation of spin waves, so it's not the same light. This is the solved mystery. In fact, the light wasn't frozen, it didn't stand still. It's a different light, the one that exists. You're still with me, I understand. If everything already seems very complicated, we've reached today's article. The fact that recently, light was once again made to stand still in a supersolid. You got it? There's a trick here, but let's get to the story. Look, the article's title doesn't talk about light standing still, but about a supersolid made of photon crystals using the power of polaritons. What are all these things? A supersolid is a material that is rigid but flows like a superfluid, meaning without friction and with completely unusual properties. This idea is from Nobel laureate Anthony Leggett. He theorized that at extremely low temperatures, the atoms in a solid can enter a coherent quantum state and can, in a sense, flow without friction through the solid. By the way, Professor Leggett was part of my doctoral committee. Here is his name in the committee, written on the thesis. And I had the opportunity to collaborate with him and publish an article together. But that's another story. In his original article, Professor Leggett argues that a supersolid would be observed by a decrease in its moment of inertia during rotation. The atoms come into a coherent quantum state, which flows like a fluid and no longer behaves like a solid block. How is that possible? Think of a glass of frozen water, which rotates as a whole and has a large moment of inertia during rotation. It's hard to set it spinning. Now, think of a glass of liquid water, where the liquid initially stays in place. When the glass rotates, because the water flows along the inner edge of the glass and is not immediately set in motion, the glass along with the liquid rotates more easily at first, with a smaller moment of inertia. Similarly, in a supersolid at very low temperatures. For the atoms to enter special collective quantum states, the atoms that form this coherent state can lag behind the rotation. Can we imagine them quantum jumping from a high position? The new article announces light that stands still, which announces how. Scientists would have created such a supersolid in a gallium arsenide crystal using light and excitons. Light and excitons would have together created some quantum states called polaritons. Moreover, thanks to some specially built structures in the crystal, it would have been a photonic crystal, meaning a crystal where the refractive index varies periodically. The polaritons were able to self-arrange in regular periodic structures, which at very low temperatures formed a supersolid. We saw how researchers created a supersolid. How is this connected to light that stands still, as the Popular Science article says? Let's take them one at a time. First of all, a gallium arsenide crystal has or can form collective electron excitations, which are called excitons. Simply put, they can be seen as a negatively charged electron orbiting around a hole of positive charge. The hole in the semiconductor is a place where an electron is missing. Light enters the material, photons, the particles of light, interact with these excitons, being absorbed and re-emitted, which tells us, first of all, that light slows down its speed. Things are subtler at the quantum level, but it's more complex than that. The structure of the crystal is designed to be resonant through some specially made grooves in the crystal, so that a periodic network of excitons forms inside the crystal. The incident light having the appropriate wavelength, continuously interacts with the excitons in a near-resonant regime, being absorbed and re-emitted, which leads to the formation of new hybrid excitations called polaritons. This is the moment when science popularizers say that light has been frozen in the crystal, that it has been made to stand still. Because the energy of the photon is stored by the newly formed polariton, basically, the initial energy is retained in a collective photon-exciton excitation state. But is it really so? Of course not. The initial photon was absorbed and its energy was transformed into something else. The formed polariton is a complex state in which other photons are generated and reabsorbed resonantly. If we destroyed this polariton and released the stored energy, would it be the same initial photon? No, of course it's another one, so we can say that the light was actually absorbed and transformed into something else. I'm upset. I wanted to make this video speaking freely. I read a few articles, I worked on the main ideas until I ended up with a script to read. That's for next time, better. What you need to remember is that the peak is not made up of classic stable objects, and photons are not little balls that enter and exit the material with the same properties. In reality, it's not the same photon, and everything that happens is governed by quantum laws and much more complex mathematical interpretations. I couldn't help but mention at the end something else that's relevant here. Photons, like electrons, are indistinguishable particles in this interpretation. We could just say it's the same photon being emitted, since photons can't be distinguished anyway. Or just as well, that the same photon is always present in the universe. Just one and everywhere. And likewise, a single electron everywhere in the universe, since we can't tell them apart anyway. This is actually one of the extravagant proposals of the Frisian Richard Feynman. That's right, the universe is made of a single electron that appears everywhere. Do you have the answer? We don't have to imagine that the world is made of objects. All we've done is reinterpret in our everyday way some complex mathematical equations of quantum mechanics. The lesson is this: we don't know what the world is in itself, we just keep describing it mathematically, just like Grandma used to knead the bread dough. And that was today's video. Until next time. Please subscribe if you haven't already by clicking this subscribe button right now. I want to thank those who support us on Patreon and those who have become channel members here. Don't forget that on Patreon you can get personalized answers directly from me.